Hello, welcome to the bar magnet lab. In this lab, we found the influence of a bar magnet across different positions in space. The purpose of the lab was to find the connection between real-world measurements and the PHYS law using a magnometer. The fundamental physics principles at play here are the PHYS law, which is the general formula down below, magnetic fields, superposition, and the unit of Teslas. The preview of the results is that the magnetic dipole was found to have a magnitude of 4.21 inch per meter squared, K was found to be 8.24 times 10 to the negative 7, N was determined to be negative 2.7727, and in our 45-degree experiment, the experimental value was 4.49 times 10 to the negative 5th amp per meters, and the computational value was 4.035 times 10 to the negative 5th amp per meters. This is about a 10% error. The actual system itself is the phone, and the surroundings include the magnet and other magnetic fields, which includes the Earth and faraway electronics. The initial conditions include the phone and magnet resting on a table positioned so that the Earth's magnetic influence on the phone is negligible. In the actual experiment, we had to compensate for magnetic north, which includes using the magnometer to find where the actual X component of the magnetic field of the Earth is as small as possible. We then had to find the magnometer chip, which we pointed out on the phone using different pieces of tape. Then we actually shifted the phone magnometer across the axis of the magnetic dipole in order to achieve desired microtesla values, and we recorded the distance at which these occurred. This is the data which was gathered from the experiment, and using the equation shown up above, we created the dependence equation below, where y equals negative 2.7727 minus 13.97. These will help us find the magnetic dipole later on. We also had to do the 45-degree experiment, so we found the distance required for 100 microtesla, and then we moved the manometer the same amount vertically. This created a 45-degree angle between the magnet and the manometer. Then the values of the X, Y, and Z B fields were measured, and we had to account for the baseline Y level just so it can be adjusted later. This is the actual code, and this whole time we were approximating the general form of the Biot-Savart law. In section 1, we actually create the magnet itself and the magnetic field emanating from there, covering all of space. In section 2, we then take the magnet and we create in all the orthogonal directions, north, south, east, west, forward, back, and describe all of those different arrows, indicating the magnetic field present at each of those locations. In section 3, we finally print everything and then also do the actual 45-degree experiment, creating a magnetic field arrow 45 degrees off. The result of this is this picture where we see the results at the bottom of the magnitude of the 45-degree arrow to confirm our magnetic dipole size, and then we also see the different orthogonal arrows and their relative magnitudes. Going through the calculations, we can see the distance dependence equation, and through that we can find values for N and K, but really we're doing this to rearrange the Biot-Savart law, setting our R at 1 meter because it's distance dependent, and through that we can find that the magnetic dipole is 4.21 amp per meter squared. There is a discrepancy between our experimental value and our computational value, however. In our experimental value, we find it to be 4.439 times 10 to the negative 5th Teslas. This is in the 45-degree experiment, and in our computational model we found it to be 4.035 times 10 to the negative 5th amp per meters. The bar magnet, the actual different models used here, because the bar magnet is very close to a magnetic dipole, the actual models should be very accurate. And so this comes down to the source of error, which with our percent error being 10%, we would expect that the source of error could actually be feasible. And these are that the phone could not be perfectly translated, as in there's some small rotation or misalignment, and there's a slightly incorrect magnometer position. So, what was observed? Well, first, when the magnometer is far away from the magnet, it measures a near zero magnetic field in the X direction. This was observed, as well as when the magnometer moves closer to the magnet, the measured X component of the magnetic field increases. So, what if you hadn't oriented the experiment to compensate for magnetic north, and instead laid it out in some intermediate angle? We would have had to compensate by changing the actual, by taking note of the original Earth's magnetic field in the X component and subtracting that from our values that we found later on. What if we were to stick two identical magnets together and run the experiment again? Because of the way magnetic dipoles interact, we have to assume that the actual strength, net magnitude of the magnetic dipole at each individual place would necessarily about double, because we're doubling the size of the magnet. So, in conclusion, we found that the mu is found to have a magnitude of 4.21 8 per meter squared, k is 8.24 times 10 to the negative 7, and n is negative 2.7727. And between our experimental and computational 45-degree experiment, we had a 10% error. All in all, we found that the Biot-Savart law is applicable to magnetic dipoles with accuracy, and that bar magnets are good representations of magnetic dipoles.